So welcome back to session 9 of our Open World Lifelong Learning course. Today we're actually going to basically complete the picture, and I'm going to say in a second what that means because we've already said last week that we have completed our picture. But there's one particular thing maybe missing presently, which is the idea of how ordering and maybe data difficulty influences our training. It's commonly summarized as a field known as curriculum learning. Before we do that, let's have a little bit of a motivation for this and recall where we came from when we ended off last week's lecture. So we started in the 7 or so weeks up to last week with the idea of continual learning, incremental learning, active learning, but mostly from what we've now realized is referred to as a closed world setting. So last week we started with the idea that if we don't really, what if we don't really know the boundary between tasks? What if we're not constrained with respect to what we test on? So we've asked ourselves the question, even if we train progressively on these 5 tasks as illustrated on the slide, what if at the point in time of training task 1, what if there suddenly are instances from task 2? Can we identify them as belonging to a different task? And so in last week's lecture, we slowly transitioned to something that we then refer to as the open world. And so in open world, the idea was that rather than just being constrained to the categories that we know or the categories that we think we don't know, but we actually already have a grasp of, this is something we don't know. What if there are a lot of concepts that are really truly unknown to us, that maybe can appear in various forms in the testing phase, depending on belonging to a different category, coming from some form of statistical distribution shift due to perturbation, and so on. So in that sense, we've retrospectively seen at the end of last week's lecture that even though we've talked about continual learning before, we've always talked about it from a closed world perspective in the sense of this diagram that when we increment with new classes, with new concepts, we've always also evaluated on these concepts in the testing phase. We've never really considered the idea that there can be various other things in the world. We've then transitioned to this idea of open world and have concluded with the namesake of our lecture, namely the concept of open world learning. We've said that open world learning, in a sense, puzzles together the pieces we've seen so far according to the definition, as you see on the slide, that the 4 tasks that an open world learner is supposed to perform are to detect the unknown, choose which points to label for addition to the model if it's in a supervised task, label the points, and update the model. So in this diagram, you can see that more or less the idea of detecting unknowns, as discussed last week, are connected to the ideas we've discussed in active learning in the center of the diagram, to the way of maybe preventing forgetting, caring about knowledge transfer in the incremental learning portion on the right. In principle, this picture looks to be more or less complete, but there's one last thing that I want to talk about today, or that we should talk about today, in order to maybe put that little bit of a cherry on top of this diagram. And this cherry will be, what if we now also in addition ask ourselves the question, what about the order in which we learn tasks? So if we have the choice to increment whatever we want, how should we choose what to start with? How should we choose what to end up with? So in a sense, it's a little bit like the question we've asked ourselves in active learning, but let's say on a grander scale from a slightly different perspective, as we'll see in a second. So on this diagram, I've just illustrated this with the arrows, assuming that you have some initial parameter learning phase with these frogs. You can then maybe acknowledge that there are a couple of unknowns that you now recognize with the algorithms seen last week. And now you have identified that there are different concepts that you still don't know about. So which one of these should you include next? As I said at the start of this lecture, the field that asks itself this question is frequently called curriculum learning. And we'll get to maybe the definition of curriculum learning first, but because I believe the definitions are not very easy to understand, we'll get to an intuitive picture pretty quickly right away afterwards. So let's take a look at the definition first before we try to make sense of it. So the original definition of curriculum learning, according to a paper from 2009 by Benjo et al., the curriculum learning is defined as a curriculum is a sequence of training criteria over T training steps, then the sequence, and each criterion in the sequence is a reweighting of the target training distribution, which is called P of Z here. In this definition, there are three conditions that then make this into curriculum learning, and it's first that alongside the criteria, the entropy of the distribution gradually increases, and so does the weight for any example. And of course, at the end, when we're at the end of the criteria, we basically arrive at the target training distribution. So it's a rather mathematical definition for something that is conceptually quite easy to grasp, to be honest. And so there is a more recent definition here, which is called generalized curriculum learning, which presents a little bit maybe of a tautology, as we'll see in a second. But all it says is that, like, let's go away from these three conditions and this precise, like, does the entropy increase, does the weighting increase, and just go with the idea that a curriculum is really a sequence of training criteria over T training steps. So this can include some designs for all the elements in the training of the machine learning model, like data, tasks, model capacity, etc. But it's really more about a strategy of how we train over time. And typically, this will be sorted according to some measure of difficulty, like going from easy to difficult, which was expressed as like the entropy, the weighting on the previous slide. In order to maybe make this as easily understandable as possible, let's revisit the example that we've seen already in the very first lecture of this entire course. And this example was a ranking language model trained both with a curriculum and without a curriculum on the Wikipedia dataset. And so frequently or regularly, the non-curriculum version is just anything as we've encountered it before. We just randomly shuffle all our data. We do stochastic updating steps. The curriculum in this case, denoted in blue in the right-hand side plot, is actually a procedure where we now start with the 5,000, in this case, most frequent words in the dataset first. And then once we start converging on these 5,000 most frequent words, we go on to the next 5,000 more frequent words in addition, and so on. So rather than randomly shuffling the dataset, a curriculum on the natural language task could be defined according to what are the most frequent words, what are the less frequent words in general, like what are the words that occur more rarely. And so on this plot on the right-hand side, you can see that initially such a curriculum training on the easiest examples defined by frequency first seems to converge more rapidly, but to a point that's maybe not so satisfactory. But at the end, starting after about 1,000 million updates on this diagram on the x-axis, we can see that the final dip in terms of curriculum here actually surpasses the version where we just randomly shuffle the dataset and do these very stochastic updates. And this is the motivation behind what we're going to talk about today. So how can we order our dataset according to some intuitive notion of difficulty, such that we can maybe do smarter updates or train in a smarter way, in contrast to just randomly shuffling all our data? And I think it's important to note, before we ask ourselves, like, what are the two central questions in curriculum learning, that such an ordering precisely in terms of difficulty is very different than anything we've seen so far in the course, because even when we've taken a look at, for example, incremental learning, when we said we first train on zeros and ones, then on twos and threes, the actual data sets themselves were primarily always randomly shuffled when we train. And also the order in which we've introduced the task, like do we first train on 0, 1, then 2, 3, was mainly considered to be sequential, or according to some labeling, more or less human imposed. So today we're going to complement this then with the two central questions that are under this umbrella term of curriculum learning. And I've kind of already told you one of the main challenges or one of the main questions in curriculum And it's precisely this idea of what is difficult. What is difficult in terms of each and every individual data instance. In the jargon of curriculum learning, this will frequently be referred to as a scoring function, or maybe more colloquially as a difficulty measure. And it's really just any sort of function that you can conceive that would provide us with an estimate of the difficulty of each and every individual data instance in an entire data set or entire data sets. Once we have such a notion of difficulty, we could then ask ourselves at least the second very important question, which is the idea of a pacing function, formally, or more colloquially, the idea of a training scheduler. In other words, it's the function that tells us how do we interleave the examples into the training process over time. So if we have very easy examples and very difficult examples, and we maybe have the intuition that it's easier to train on easy examples first, and it's more challenging to go towards the harder ones, then at what point in time do we introduce new examples? So you've seen on the previous plot, and we'll revisit this in a second, that we could, for example, start converging first on an easy set before introducing a new one. But arguably, there are various ways in which we could now think of this challenge, and this is typically summarized under pacing functions. So to put this together, what curriculum learning would regularly do or regularly investigate is summarized in this algorithm on the top right on the slide. Assuming that we have a scoring function which is referred to f here, some data set which is referred as x, and some form of pacing function, what we can think of is we can at any point in time, we can think of expanding the size of our data set with new examples. We can then do our uniform sampling of batches within that subset of data. And we can get some result, and we have to decide with an overall sort of pacing at which points in time we do this. So let's start taking a closer look at this idea with the notion of what we could refer to as something like a predefined curriculum. So predefined meaning on this diagram that given a training set or given a data set, we assume that we have a difficulty measure, so some function that gives us the difficulty of each and every instance, and we apply this difficulty measure on the entire data set first, sort the data according to difficulty, and then put this into a training scheduler to start model convergence on different subsets. So it's a little bit inspired by what I would like to call textbook style learning. I'm sure there's a formal word for this, but essentially the way that maybe we as humans in parts learn when we are confronted, for example, with learning a new language in a class. Like someone gives you a textbook and tells you that in chapter 1, it's most likely that you'll learn how to say hello and how are you before you get to like really complicated grammatical concepts, maybe things like tenses, future tense, past tense, etc. So this would be the idea here, that we kind of have this like predefined curriculum in a form of like a textbook style. And we can then, of course, ask ourselves the question, if we assume the style of learning, we'd start with maybe a small and easy subset of data. And over time, we'd like to append this with the harder subsets, the harder examples. So on this diagram on the left-hand side, you can see that it's illustrated on the apples and oranges example, where maybe intuitively easy apples and oranges are ones that are centered, large in images, no backgrounds, whereas the harder you go, you could think of, are there variations of apples maybe with different colors? Are there multiple apples in an image? Do they have a different shape, etc.? And so the main question here then, or one of the two main questions that we've just said is, how would we define such an easy subset and a harder subset? How do we assign a difficulty score in such a textbook style curriculum? So the question here is to get creative essentially and think of ways to define difficulty with respect to each and every instance in a data set. And so at this point, I'd like to encourage you to pause the video essentially, think about what ways you can think of how you could perceive difficulty in a data set, maybe what that even means, the different perspectives of how you could think about this. You can get inspired a little bit by this idea of, for example, frequency of words, like word occurrence, as we've had in our motivating example. But I'd really like to encourage you to pause and maybe for 3 minutes or so, think about this for a little before I show you a bunch of things on the next slides. So assuming that you have thought about this for a second, and feel free to like send messages in the chat as well if you want to, there are a couple of notions of difficulty measures, or more specifically, like the metrics according to which one could think of difficulty for specific data types, illustrated in this table on this slide from a recent review survey style paper. And the main thing you can already see here is, first, there are a lot. Even in this table, there are already a lot of difficulty measures on the left-hand side. Each of them maybe follows a slightly different angle by which this difficulty is defined. So, for example, we could think of difficulty as an idea of things get more complex, maybe things get more diverse, maybe things get more noisy, etc. But also, it's important to already acknowledge at this stage that difficulty for datasets is somehow inherently a very data type specific idea. So in the sense that if we think of word frequency, for example, or sentence length as a way to measure difficulty, it's very specific to text, whereas maybe number of objects is very specific to an image. If we think of programming, for example, we could think of nesting of operations. So in that sense, defining difficulty will be specific to the type of task and the type of data we look at. I don't want to spend too much time on the slide here. I'm mainly just illustrating this to give you the idea of various ways in which difficulty could be posed, but primarily to make this make it clear that when we now continue to think of difficulty on the next slides and how to define it, it will be something that's very specific to the type of data and the type of model, the type of task we consider. So is difficulty task and model specific? The answer to this is yes, it actually is. And we've already seen on our motivating example that specific tasks do in fact allow for very specific definitions of difficulty. So just to recall this, to really let it sink in, on this example of natural language translation for here, we could in fact think of word frequency or sentence length as one way to measure difficulty. So what we do is we take, for example, the sentences on the very left, we'd give each of them a integer value according to the length the sentence has. We'll then do something like a histogram of the sentence length versus the frequency. And then we could turn this, if we want to turn this into a like normalized 0 to 1 difficulty score, we could use like the cumulative distribution function as a empirical fit to have a normalized measure of difficulty. So the sentence, thank you very much, with a length of 4, maybe would have a very small difficulty, not 0, but close enough to 0. Whereas complex sentences like what did she say when she was referring to, and so on, maybe has a very high difficulty because it, in translation, it entails the idea of having like complex grammar and conditional sentences and so on. We can similarly intuitively think of this task specificity of difficulty measures if we take a look at images for a second, where arguably, again, maybe intuitively, it becomes clear that an easy example for semantic segmentation would be something like on the top left, where a bird is on a rather plain background, whereas if we go towards examples more towards the right, with a lot of clutter, a lot of entropy in the image, lots of objects, lots of tiny objects, it maybe intuitively becomes more difficult to semantically segment this. And lastly, we can realize that there are various dimensions to difficulty, and it's not just basic data statistics. So on the intuition side, we can think of basic image statistics like word frequency, we can think of sentence length, entropy in an image, but there are also other more high-level, more abstract ideas that may influence difficulty, and especially concepts that maybe we as humans will find difficult or not difficult, which is then the question of how machine learning models relate to this. So on the slide, you can see some maybe other forms of difficulty measures or influences for difficulty measures, where an idea, for example, on the very right-hand side is context that factors in, like something that is extremely surprising to you, where maybe the tree is in the water, which is not very expected, and maybe now it here says in the caption, a boy with a beard, which is something you wouldn't expect because beard and boy isn't really semantically supposed to be like that. And so maybe you would be surprised, and so you have an unusual pairing that would also be some form of difficulty measure. And so let's ask ourselves actually what is in fact difficult and what is not difficult. And let's look at a couple of examples to get a better intuition for this. We'll start with two examples where we'll ask ourselves a little bit the question of how is difficulty working out for machine learning models, but also how is difficulty, what is difficulty from the perspective of human perception? And so a little bit of a disclaimer, of course, is that keep in mind that I am in fact a machine learning researcher, a computer scientist, not a psychologist nor a cognitive scientist, but I'll do my best to present two studies to you and summarize them so that we can get a little bit of the inspiration from the human perception side as well. So whatever I'm going to say is going to be factually, hopefully correct with what is written in the respective papers, but do take it with a little bit of a grain of salt. So in this particular first example here, we can take a look at human memorability and its correlation to image statistics in a second. So human memorability meaning that there has been several experiments with humans where the idea is that for 1 second an image is shown, for 1.4 seconds there's a blank, and then you repeat this with a different image shown, another blank, a different image shown, and so on. And the task is to essentially buzzer whether the image you're now seeing is one of the images that you have recently been exposed to. So just saying basically in a memory repeat as shown on the right bar here, you'd have to buzzer that this is an image I've previously seen within this time frame that you are given in this image, this like 1 second. So it's a, let's say, decently short interval in terms of overall scale, but to the best of my knowledge, a rather long interval with respect to cognition, with respect to what is expected, how long cognitive processes take. And in order to maybe make sure that this isn't just that whatever you're measuring in terms of how accurate humans are in figuring out what they memorize and what they do not memorize, there is something that is called vigilance repeat here, where you do the same thing and people are still supposed to buzzer, but it's like a separate set of examples that is like your control set, where you just make sure that the humans are attentive. So you're supposed to, like, you're measuring this to make sure that whatever you're observing is not just that this human like generally performs poorly or this human generally performs very well and so on. So it's like a little bit of control in the experiment. So we can do this with a lot of humans, or people have done this with many humans, and then you can figure out what the instances are where basically you mess up, what the instances are where you don't mess up, and so on. And you can then go on and try to see, according to this criterion of like memorability, like how memorable is an image, whether that corresponds to if it's difficult or not. So you assume that basically images that are very memorable are less difficult than images that are less memorable. And you could now try to correlate this either with what other humans think, and you could try to correlate it with some of the basic image statistics that we have essentially already suggested at the start of this lecture would potentially be meaningful as a measure of difficulty. So you see a correlation factor here. It's not that important, to be honest, which precise correlation measure it is. Let's just go with it's a correlation measure. And on the very right-hand side of this table, you can see the correlation of humans with respect to each other. And this correlation is actually quite large. So it's 0.75 here on a normalized 0 to 1 measure. And so in fact, it seems like the images that are identified as memorable do overlap quite substantially for different humans. So there is a certain form of agreement of what humans consider memorable versus not memorable. And we can ask ourselves now how different image statistics and factors, what role they play. So more specifically, think of this like a regression. So take the all the data set, sort it according to this metric, for example, of object counts, and see how this then correlates to a sorted version according to the difficulty that humans had in memorizing these examples. And so you do in fact see that some of the factors in here, if you do sort it that way, correlate, but others do not. More specifically, apparently object counts and object areas seem to play quite a small role in terms of being correlated with this human way of memorability, whereas other factors, maybe like the scene category, or the fact that it's objects and scenes, does play a more important role in terms of correlation. We'll take a look at this more specifically in a second experiment, which I think is a very nice follow-up, or let's say a different perspective on the same idea, where people have taken a look not at the memorability of images in this experiment, but they've taken a look at response times instead. So more specifically, the idea is to now collect the response times where an experiment is set up with human evaluators using a protocol as illustrated in this left-hand text. And I'm just going to read it out. So the first step I is we ask each annotator a question of the type, is there an object class in the next image? So essentially, there are 20 classes in this Pascal-Bock dataset from which an object could originate. And before being shown an image, you're asked the question, search for this particular type of object class in the next image. You're then being shown the image and the time, and you again have a buzzer, like a yes or a no, like is this object present in the image, is it not present? And the time until you hit the buzzer, hopefully correctly, is recorded. You'll do some, maybe when you do the study, you'll do some cleaning in the sense of let's only take it humans who have a decent set of examples on a validation set correctly, so you don't just record response time where everyone just buzzes no all the time very quickly and gets everything wrong. But assuming just let's take the set of humans that do this correctly on a large average and see what the response times are for a lot of individual images. It's, in a sense, similar to the memorability experiment, but a little bit different. Here it's really about the idea that difficult is defined by how long it takes you to find an object in the image. And you can, again, do the same type of analysis. It's not really much of an analysis, the same style of comparison, where you try to think how different image properties correlate with the response times. Meaning that if you sort the entire dataset now according to response times of the humans, assuming that response times that were really small indicate an image being very difficult or, very easy, an object being very easy to find in an image, and long response time being very sort of indicative of difficulty, you could now sort this according to this response time and again compare how it correlates with a sorted version of the same data set according to, again, number of objects, or maybe the non-centeredness of objects, like are they centered in the image, are they somewhere else, and you could see how it correlates. You can see the correlation coefficient again here on the right-hand side in this table. And first of all, I think it's interesting to see that there are some correlations in fact. So for example, for a number of objects, you do see a positive correlation of 0.32. For the mean area covered by objects, maybe you see a negative correlation, meaning that it's inverse, like whereas the response time grows over time, you think it's more difficult. The mean area covered by the objects is enlarging, that actually gets more easy. So it's inversely correlated. But quite crucially, it is correlated. but also somehow maybe it's less correlated than we would, at least I would partially expect. So non-centeredness, for example, like is an object at the center or is it somewhere on the outsides of the image, does not seem to be fully correlated, where I would have at least intuitively expected it to be a good indicator, assuming that maybe if you see an image, you always look at the center first. But I guess due to the way that saccades work and eye movements kind of stochastically saccade, maybe it's not so much the case. So you could repeat this experiment, or you could, let's say, not repeat this experiment, but you could extend this experiment to all the various ways in which you could think of difficulty and the notions of basic statistics that you think are correlated with difficulty. So maybe you could think of number of edges in an image, for example, number of segments in an image, the objectness, like how large sort of is the image, or how wrong is the bounding box in terms of how much of the image versus how much of the objects versus how much of the background it encompasses. And you could try to analyze these correlation factors. You'll see, first of all, which is good to see, that if you just assign random difficulty scores to all the data set, you'll find that there is quite a small correlation, close to none, which is good because otherwise you could just randomly assign difficulties. Some others, like image area, image file size, have close to zero correlation as well. Maybe edge strength becomes more important, and maybe number of segments as well, and so on. But quite crucially, again, what we can observe from this top right part of the table is that these extremely, let's say, basic notions of statistics of an image, of text, and so on, only have a very partial correlation with the way that humans seem to have difficulty in terms of either this memorability task or this search style response time task. What you could now think of in addition, which has been done in this particular paper, is you could take the human response times and assign them as like something of a label to the data set, and now formulate this as a regression task. So train, for example, a deep neural network that is supposed to predict the difficulty of an image in terms of is it difficult for a human or not, by regressing on these labels. And already by just doing that, you can see that this improves the correlation quite significantly in contrast to the preconceived ideas of basic image statistics that we could formulate alternatively. In addition, what comes into play is that, so what we're seeing on the last slide is basically machine learning models may have an idea of how humans interpret difficulty, but human difficulty and basic image statistics may not necessarily correlate to the degree that we would expect it to. What we could now also ask ourselves is the other way around. What is difficult for machine learning models that may not be so difficult for humans, or is difficult for humans, but independently, what's difficult for a machine learning model? And a very interesting experiment that has been done here is the idea to figure out whether deep neural networks, or like very complex hierarchical models in general, how they compare to more shallow models like a support vector machine or a random forest. And so an experiment that people have done is they've taken a look at an ImageNet, for example, data set. They've trained a support vector machine on it. There's a certain amount of images that you get correctly by a support vector machine. There's a certain amount of images that you mess up, where you make mistakes. And then when you train now a second model on this data set, something like a deep neural network, which you assume is more complex of a model, you could figure out in the training phases which of the examples that the more shallow model got correct or got wrong are learned by the neural network first. And so you can see the ratio on these plots here illustrated on the slide, where in each of them there's a particular deep neural network model, a convolution neural network on the left, a dense-net, which is also a particular style of deep convolution neural network in the center, and the ResNet, a different form of deep convolution neural network on the right-hand side. And what is illustrated is the ratio of the accuracies of the deep neural network with respect to the correctly classified support vector machine examples and the wrong subset. And as you see here, this ratio is very positive, meaning that especially in the beginning on the very left-hand plot, this ratio is very heavily going towards 7, and then over time it goes down. And so what this means is that empirically speaking, the deep neural network starts to learn the example that the SVM, the support vector machine, also considers correct first. And in other words, this then means, and that's the conclusion of this particular work, that shallow embeddable examples seem to be learned first by even deep neural networks. A second thing that then comes into play is that various machine learning models, they work in different ways that humans work, right? So surely already the slide before tells us that shallow embeddability versus deep embeddability is very different in terms of style of thinking when considering difficulty, if in contrast to thinking about response times or in contrast to thinking about basic image statistics. And an additional factor that comes into play here that makes it even harder to think about difficulty for machine learning models is that we don't really have too much of a notion of how machine learning models often work. So on this slide, what you can see is essentially frequency selectivity or frequency invariance. And it's basically defined in the following setup. So you can take a look at a neural network or any classifier, and you can introduce small adversarial perturbations along specific axes. And then you can measure how much of a perturbation you can induce before the output, before the function starts changing. So in other words, how much of a perturbation, how much of a change can you introduce while the model still stays invariant to this perturbation. And so this particular work here has done that on the idea of frequency, where in images they've taken a look at high frequencies and low frequencies and figured out if they change on the low frequency side versus on the high frequency side, does it introduce a change? And so on the right-hand side in this curves, you can see on the top one what happens or how much of a margin, like how much of a perturbation can you introduce before the function does in fact change, seeing that for low frequencies here, there seems to be very little of a margin, like very little of a change required in order to result in a different output. Whereas for very high frequencies, it seems like the model is more or less invariant to this. Meaning if you change a lot of high frequency components in the image, it does not really matter for the particular classifier here. And just to be on the safe side, the same experiment was repeated on the bottom in the red curve, where the image was flipped, so the frequencies are exchanged, where you would now hopefully expect the plot to be the reverse. Like if you change low frequencies, the function it's pretty invariant, and so on. So long story short, what the slide is supposed to tell you is that machine learning models can in fact be invariant across different axes, and we may not know about this very well. We may not have a very good understanding of this. So in other words, if we think of difficulty from a frequency perspective, we could perhaps postulate the idea that images with a lot of low frequencies are easier to classify maybe than images with a lot of high frequency content. Or maybe we could think of the opposite. However, the problem is if our model has a specific invariance to one of these features, meaning it does not actually care about this feature at all in discrimination, then this notion of assigning difficulty to the dataset is quite meaningless for this particular model. So to give a little bit of a sum up of the idea of difficulty, there is difficulty in the way that humans perceive it. There's difficulty in the way that humans memorize, that humans have respond to a query in terms of how long they take. This difficulty may be slightly correlated with basic image statistics, but maybe not to a full degree. Machine learning models could perhaps estimate this difficulty by training on regression. But on the flip side, it seems that some measures of difficulty could help machine learning models, but others maybe not so much because the model may be invariant to it. So it's a real challenge to figure out what are the particular measures of difficulty that we need to find in order to do curriculum learning, given a specific type of data, a specific task, and a specific machine learning model. To wrap up the discussion on difficulty before going on to the idea of pacing, we can also keep in mind that difficulty is not just the question of how difficult it maybe is to classify, how difficult it is to predict, how difficult it is to train. We could also think, for example, as difficulty as an interesting idea when we consider tasks such as annotating images. So semantic segmentation is quite close to this, where we could maybe think of which dataset instance is more difficult to annotate even for a human being. So in this What's It Going to Cost You paper, the idea was to predict sort of the trade-off between informativeness of a particular image versus the effort it takes to label it. And so I think it's interesting. We're going to see at the end of the lecture that there is a correlation, of course, between curriculum learning and active learning. But quite crucially, already here, I want to emphasize that the key difference between active learning and curriculum learning is really in this idea of difficulty versus informativeness. So in active learning, we've also asked ourselves the question of ordering a little bit, like which elements of a pool do we query next? But it's always been primarily from this perspective of what's like the most informative example that we can take next. It's not really been explicitly from the idea of, is this informative example an easy or a hard example? So before we wrap up at the end and give a little bit of a, of course, complete story again, let's take a look at the second half first. And the second half is going to be about the central question of assuming that there is some sort of notion of difficulty and we have a way to assign difficulty, let's figure out the pacing or how to schedule the training. And so in this left picture again, if we assume that these yellow, green, and blue boxes are figured out, meaning we do know what the small and easy subset is, we do know what the slightly harder subset is, and so on, we'll ask ourselves the question what the training process on the x-axis looks like here, like the Q1 to Qt, in the sense of when do we introduce these more difficult examples. Naturally, again, and as always the case, there are various options and heuristics that are now conceivable. Perhaps two of the easiest I'll talk to first and illustrate on this slide are, on the one hand side, what is called a one-pass curriculum. So in this algorithm here, what we have in lines 2 and 3 is that there is some sort of notion of difficulty measure that we can use to sort the data set into k chunks of increasing difficulty. And what we could now do is take these buckets and introduce them one by one in lines 5 to 7. And while we have not converged on one bucket, we do not continue to the next. It's a little bit like incremental learning in the sense of that if we had 10 different classes, we'd figure out what the easiest class is first, we train on that, and then we train the next difficult class, and so on. But quite crucially, in 5 and 6, we see that the data set is not necessarily concatenated, it just grows in terms of difficulty. So coming back to a language example at the beginning, where we said, for example, word frequency is a thing, we'd actually start with sentences that don't have that have very frequent words, or sentences that are very short, and then later we just replace them with a different chunk of data sets. On the intuitive sort of same style, same type of idea, but maybe slightly more realistic in terms of performance, is what is called baby steps curriculum. It's essentially the same idea in lines 2 and 3. So we have a difficulty measure. We sort our data set into k buckets of different difficulty. So we discretize our difficulty curve into bins. And then we now again start introducing the first one until convergence. And after we've converged, we start concatenating the next bucket into the data set. So it's really this idea of like progressively growing the data set, but progressively growing it in a way that each increment presents the next set of slightly more difficult examples. And now naturally we could go wild with this. So assuming that it's not just about K buckets and all of them are uniformly same size, all of them converge always before introducing something new, we could think of pacing functions similar to how we think of learning rates. They're schedulers that we can think of. We can think of maybe some sort of exponential pacing where we start really slow and then go really fast, or we could think of the reverse where we start really fast and then introduce the extremely difficult examples only towards the end in some sort of square root function, as illustrated on the right hand side. Now, in principle, we could go into a lot of details about these pacing functions and which one is more correct, which one is less correct, if there even is such an idea as a more correct pacing function. But let's take a look at it from the utility side. And so from the utility side, we have a natural language example in terms of language translation here in two plots. On the left one from French to English translation, on the right one from English to German translation for two models, a recurrent neural network and a transformer model. And in essence, what we can see is that it's not straightforward to choose the pacing function. The pacing function that you have illustrated here are, on the one hand side, this single step curriculum, and on the other hand, you have the different style of pacing functions like a linear or a square root, and you have the baseline, which is called plain here. So the blue line that is called plain is essentially the training without a curriculum, meaning that we would shuffle our data set and we just train on whatever the shuffler gives us at any point in time. The good news is this blue curve seems to be performing worse than any of the curriculum curves. So if we take a look at any of these plots, we can see that overall at the end, the absolute performance of the blue line is always a little bit worse than the other curves. But also if we take a look at the x-axis, at which point in time a specific performance has been reached, the blue line performs worse. So if we concentrate on one particular example, namely the second one from the left, the transformer example on the French to English translation, we can see that this effect is quite dramatic actually. So on the dashed curves, the difference between 36 and 34 is the absolute sort of performance gain that you get by introducing a curriculum. And on the x-axis, you can see two vertical lines that tell you how much faster a specific point in time of accuracy, mainly the final accuracy of the blue curve of the plain curriculum, or rather the non-curriculum, is reached if you introduce a curriculum. So roughly speaking, maybe you have about half the amount of steps here to reach the final performance with the curriculum, in contrast to the one where you have excluded a curriculum. And this is quite interesting. And it's the main sort of promise of curriculum learning, that not only do you reach a absolute performance maybe that is better, but maybe at some point you could also reach it faster. On the not so positive side, you could actually also see two things. So first of all, whereas this seems to work very nicely for the transformer, it does not work so nicely for the RNN, given in this particular example, difficulty being associated with, in fact, sentence length and word frequency. So whatever you get in terms of benefits in the curriculum for the transformer, you do not seem to consistently get for the recurrent neural network, supporting our previous slides that difficulty and curricula are inherently not only tied to dataset type and task, but also to the specific model we choose. And on the second, maybe not so positive side, is that the different pacing functions that you have illustrated here in the various shades of red and orange do not actually seem to be making that much of a difference. So in other words, if you think of some of the pacing functions going really steep in the beginning, so introducing a lot of examples at the start that are fairly easy, and then the most difficult examples only later, in contrast to maybe a linear curriculum that just goes through buckets one by one sequentially in uniform size, you can see that this does not seem to be making too much of a difference in this particular example. In other words, difficulty is a challenging to think about concept because it's not very intuitive how basic image statistics work in terms of, basic data statistics, not just image statistics, how basic data statistics work in terms of machine learning models and how they are factored in. It's difficult because we don't know whether human recognition and human difficulty assignment correlates with that. And we've seen that it correlates partially. But on the pacing side function, we have a similar challenge in the sense of that it's not very intuitive for us to figure out which pacing functions are maybe better than others. So in quite a lot of works, you'll find that this idea of a baby curriculum or baby step curriculum, in a sense of just making K buckets and then just introducing them one by one whenever we've converged, is a quite popular approach still. One of the limitations, perhaps, or just an interesting thing to think about, is that so far in today's lecture, we've talked about curricula in the sense of that we assume that they're predefined. So predefined curriculum in this textbook style, as I've mentioned at the start, meaning we have a pacing function that we came up with where we say like when difficult examples are introduced, we have a difficulty measure slash a scoring function that initially sorts our data set so that we can introduce it in these buckets. But what if we start thinking about moving away from such a predefined curriculum and thinking about other ways how we could maybe define curricula on the fly based on the models we have at hand? So the intuition here is that we've just sort of noticed that curriculum learning is an inherently model-specific thing. It's not just about data difficulty. It's not just about human difficulty. It's also about task difficulty and specifically the particular model that we have at hand. And so what if we start factoring in our model and going away from this idea of like a predefined curriculum that is conceived by some notions of like predetermined difficulty and so on. So what we've just talked about was this illustrated diagram on the top here that is called predefined curriculum learning. And what we're going to talk about next for the remainder of the lecture are a couple of popular approaches, mainly two, to keep it a little bit focused, of how we could get rid of this notion that we need to absolutely use some preconceived ideas of difficulty and sort our data set up front and then have this like bucket style learning that we've just talked about. And so the first of these two maybe will still fall into this idea of predefined curriculum, but it falls into a different category of how we measure difficulty, perhaps. And so instead of defining the curriculum ourselves, let's make the first step and think about the model or a pre-trained teacher model that we could use in order to measure the difficulty of particular instances. So recall that perhaps inspired by this idea that models are pretty good at regressing on human difficulty, we could also think about using a pre-trained machine learning model on particular types of data to use as like an external source to assign difficulty to the dataset instances that we see in some other form of training. So in a sense, this is related to transfer learning, and that's why you would maybe call it a transfer teacher curriculum. But really the idea is that still in a predefined curriculum, you could have a training data set and a difficulty measure, but this difficulty measurer is in fact a pre-trained model that sorts our data. And so on the right-hand side, you see an example here actually on image classification on ImageNet, where this idea of a teacher-based curriculum is taken into account. So the curriculum is the blue curve, where the pre-trained model essentially tells us which of the elements are difficult, which of them are not difficult, according to how like well it predicts. The vanilla is like the regular one. The anti-curriculum is actually also interesting. In red, it would be the same idea of sorting according to difficulty, But somehow going from this idea that difficult examples are really necessary to be trained first, because maybe the intuition is that we maximize our knowledge gain in that way. Interestingly, you can see that the anti-curriculum does not work that well. Maybe that's not very surprising. But also you can see that the blue curriculum, now not defined by like basic statistics of the data, like length and frequency and edges and so on, but based on what a different machine learning model thinks, performs quite well. So it's kind of maybe inspired by this one example that we've seen on support vector machines and random forest, where the idea is really that machine learning models themselves could give us a good notion of what is difficult and what is not difficult. And so in fact, a let's say popular variant of curriculum learning that is often used has a different meaning, where the idea is that instead of using a teacher model completely as a separate source, we could just use the model that we're learning currently as an adaptive difficulty measure. So in other words, how difficult are specific examples for the particular models we're currently training? So moving away from this predefined notion of curriculum, whether it's according to instances, according to basic statistics, or according to a teacher model, towards like the competence of our model at a current point in time. So it's easiest understood if we look at this diagrammatic illustration at the center of the slide, where the main difference to the same diagram that we've seen before is that the red arrow that really has this loop between the model trainer, the training scheduler, is now extended to the difficulty measure as well. So previously, we would have ranked our data set and sorted it once, and then feed in the like different chunks of data according to a training schedule, according to a pacing function. But now we could think of replacing this entirely by just saying that the difficulty gets reassigned at every couple of steps of machine learning model training, by taking into account how well a model performs on the data instances at a given point in time. Perhaps it's easiest to think of this as just taking a look at the loss. So if you have dataset examples that decrease the loss quite rapidly in the beginning, maybe these examples are easier to learn than the ones that are slightly ignored by the model, the ones that result in very little change in loss at the start. So one idea could be, for example, to self-pace the model by prioritizing the sampling of instances that are fast to learn. And in fact, that is what basically self-paced learning does. It's often then called not only curriculum learning, but self-paced learning, because the pace of the model is somehow determined by the model itself. So it's self-paced by taking into account that there are different instances at different point in time of model training that are easy to optimize versus hard to optimize. The crucial difference really here is, in contrast to the curriculum learning that we've seen on all the previous slides, is that rather than relying on some sort of ranking according to like the target hypothesis on which we want to end up, we actually now rely on the model's current hypothesis at any point in time to assign a measure of difficulty. So the teacher sort of style teacher curriculum would really be about a target hypothesis, but the self-paced learning would really be about taking into account the current hypothesis of the model we're training, which we use to score the difficulty of each and every single instance and pace the learning. Now, before we get to a second version, we can just briefly see on the right-hand slide, on the right-hand side of the slide, that this does in fact work not so well. So the red curve is self-paced learning, and you can see that in contrast to a blue curve, which we'll call self-taught, which we'll explain in a second, it actually performs rather poorly, especially even in contrast to vanilla, so the sort of plain non-curriculum style idea, where we really now underperform in this self-paced learning. So although self-paced learning is maybe a very interesting idea, measuring the difficulty of a particular instance according to the current loss or the current predictions is not possibly the smartest thing we can do. And I think if you've listened to the course over the last couple of weeks, it may be slightly intuitive of why this is the case if you think of the correlation and relationship actually to what we've seen in active learning. In active learning, we've kind of done almost the same thing. So self-paced learning and active learning are maybe not so different. At least if we do active learning from the perspective of querying new data instances according to various heuristics on predictions and uncertainty. And so recall that in active learning, we said that if we do in fact use predictions as a heuristic for what to query next, there are various pitfalls that we can get into, like overemphasizing novelty, overemphasizing noise, all these kinds of problems that would now maybe also come into play when we think of self-paced learning as the current loss or current predictions forming the basis for a difficulty measure. An interesting alternative that I would like to present, or that this paper also talks about, is something that is then not called self-paced learning, but self-taught learning, similar to this teacher curriculum that we've just seen 2 slides before, but not based on a separate teacher model, but based on the model itself. And what we could think of here is that the issue in self-paced learning is that the measure of the difficulty according to the current loss or the current prediction is quite volatile because it changes at every single step during training. So maybe the error that we initially may make in assigning false difficulties and introducing examples too early or too late snowballs quite rapidly. It accumulates quite fast. So instead, we could think of a different version of like self-paced curriculum learning, which is self-taught learning, where we first train a model fully to convergence on the entirety of the dataset. Then we measure each instance according to the final model, assign the difficulty score, so in the sense of a sorted, then predefined curriculum, and just start over with the curriculum now. So we repeat. And then we can do this a bunch of times, which is in a sense a little bit related to prior ideas in boosting that I just want to mention if you are aware of like what boosting is. So self-taught learning then maybe is also a form of curriculum learning, but the curriculum is defined on like a larger loop in that sense. Like you train the entire model to convergence, you assign the difficulty scores, you start over, you train again, you assign difficulty scores. And theoretically, of course, you could repeat this infinitely many times, but practically speaking, you'll see a natural sort of convergence to no longer having any benefit after you've repeated the cycle a bunch of times. So to finalize today's lecture, and I realize I'm going a little bit faster than usual today, but let's ask ourselves the question, does intrinsic ordering or pacing actually exist? And the reason I'm asking this question is, I'm not sure if it's intuitive to you already, but if we can use the loss of a model as a measure of difficulty, does this perhaps also mean that the model intrinsically orders examples during like regular shuffled training to some degree as well? So naturally, if we can think of self-paced or self-taught learning as the loss is telling us which examples are difficult, which examples are not, then the question is, are those simple examples maybe also learned during training first, even if we shuffle the data, because they're just simpler to learn? And I think this is not a very far-fetched sort of question. I think it's a quite intuitive question, at least to me. And we can take a look at a bunch of experiments that maybe support this hypothesis in various different ways. First, by taking a look at what happens when we train multiple models, specifically here in a second, multiple neural network models, and first check how similar their representations are. Now, of course, why is this interesting? Just to repeat for emphasis, recall if you revisit lecture 2 and the slide summary of an overview of mini batch stochastic gradient descent, for example, is that we typically use mini batches and a stochastic gradient descent version where essentially the data is shuffled differently in every epoch. So we loop over the entire dataset once in one shuffled version, and then in the next epoch, we loop over the dataset again in a differently shuffled version. So each and every single mini batch consists of a different subset of examples that constantly change over time up to the point of convergence. So if we take a look at then two, for example, convolution neural networks that are trained on such a randomly shuffled data set with different initializations, we can then ask ourselves the question, how much do the representations that you end up with after training, how much do they relate and how much are they uncorrelated? So a fully matching representation, as illustrated in this diagram here, would, for example, be these two green filters on the very left. Some slightly correlating examples would be these edge filters more towards the right that maybe are the same edge, but in like a very slightly rotated fashion. And maybe there are then other patterns like high frequency patterns that are overall less correlated in the sense of that although two models learn different frequency selectors, they do so in different ways. We can then make a quantitative measure out of this by doing something like a bipartite graph matching. So we take the representations of two neural networks, we start with the representation of one neural network, and we figure out of all the options in the other representation of the other network, which of them fits. We pick the one that fits best, and then we basically lock in this match. We proceed to the second feature and see out of the remaining options which one matches best next, etc. We could also do this in a semi-matching way where we don't sort of take out the option, but we can match multiple features maybe to one, assuming that there's some sort of redundancy and so on. And so on the right-hand side in this plot, you can see on the x-axis what this bipartite matching looks like for different layers. So going from the early convolution layers to the late convolution layers in this particular architecture. And on the y-axis, you can see the average correlation between the initially randomly sampled initializations and randomly shuffled dataset training after convergence. Maybe rather intuitively, you can observe that the correlation is extremely large, like 70%-ish on the first layer, and then it kind of degrades a little bit towards the later layers. I think, first of all, it is interesting that there is such a high correlation, but it's also natural maybe that this correlation decays over the layers. And that is because if you recall what we said about deep neural networks in the transfer learning lecture, we said that knowledge transfer in deep neural networks often works because the very early layers learn representations that are quite generic in terms of like an edge filter that could be useful for various types of data sets. And maybe they always kind of emerge in one way or another, independently also of what data we've seen to some extent. But most definitely, if we just shuffle the data sets, we'd expect maybe to still learn the same sort of edge filters. If we go on to the higher layers, we potentially expect this correlation to be less specific because there are a lot of different ways in which we can arrive at the same decision. Like if you have like a super large amount of parameters, there's almost infinitely many ways in which you can do decisions. So maybe the correlation drops as you proceed deeper into the architecture, which was why in transfer learning, maybe we also said that these layers are less useful for transfer. We can take this experiment one step further and ask ourselves not only the question of if we train multiple models, multiple neural networks of the same or maybe even different type, we can not only take a look at what their representations converge to at the end, we can also maybe take a look at how they agree on the individual instances that they get correctly at a precise point in time during training over time. So what I mean here is illustrated in this diagram. On the x-axis, you kind of see three panels that are supposed to indicate three different points in time. On the rows, you see three different example illustrations of an owl and two cat images. And in each of these boxes, you see what the predictions of three different models labeled M1, M2, and M3 could look like. So walking through the very first box, you could, for example, see that the owl image is correctly classified as an owl by model M3, but incorrectly classified as a cat by models M1 and M2. Naturally, this would mean that if you calculate the accuracy of the model, then maybe the first one is not accurate, the second one is not accurate, and the third one is accurate. So if you just average the accuracy, you would get the impression that you maybe arrive at a score of 1/3. But instead of just looking at the average accuracy over these three models, assuming that one is correct and two are wrong, you could also take a look at instead of how much they agree on what they predict. So in the center panel, we could see the same picture again, maybe at a later point in time, where the first two models now correct their mistake and also predict that that the first image is indeed an owl, not only giving them a particular measure of accuracy, but also now saying that these three models that we've chosen at this point in time of here, epoch 2, agree on this particular example in the sense of that they provide the same prediction. And we could see this in this green box in terms of a positive agreement, but we could also think about negative agreement on the bottom example of the cat, where maybe if we have like 1,000 classes to choose from, we could still ask the question, do all models make the same mistake? So do they agree on the negative parts? Do they make the same mistakes in prediction at a particular point in time? So in addition to accuracy, we could maybe calculate such a score where although maybe the accuracy is 1/3 or 2/3, we could maybe agree on half the examples or maybe all of the examples independently. And then we can plot this agreement here for the positive examples, so for only the correct examples, in different plots where we have trained multiple models over time. So on the left-hand plot here, you can see the same model, or more precisely, 5 types of the same model, so different random initialization and different data shuffling during training. You can see how their average accuracy is. Given that it's the same model type in terms of architecture, it actually performs quite similarly, so the standard deviation around the red curve is quite small. But we could now also take a look at the blue curve, which is this agreement score for the correct examples that we've just defined. So first of all, we can see that this blue curve rises according to how the red curve rises as well. And naturally, this is very unsurprising. What is equally unsurprising is that if we reach 100% accuracy, then quite obviously by definition, the agreement of all the models must be exactly the same. What is maybe more interesting is the part at the beginning of the curve, in particular, these epochs from 0 to 12. There is a curve that is called lower bound here in green, which indicates essentially how much agreement you would expect in the worst case the models to have. So more precisely, if you have 5 different models, for example, and at epoch number 12 here, you have an average accuracy of 80% in each model, then there's 20% of the data set that each model gets wrong. And given that there are 5 models, you could now think that the worst case scenario in terms of agreement that could happen is that each of the 5 models gets a different 20% of the data set incorrect. And in that sense, the agreement, the expected agreement here would be 0, because all of the models mispredict different 20% of the data set. So observing here that the agreement in fact is more close to 60% actually means that there is quite a strong sort of agreement in these models that is way more than you would maybe expect intuitively, or maybe you do expect it intuitively, but it seems to be a trend. More interestingly, on the right-hand side, this trend actually persists when you take different neural networks. So maybe it's a little sort of expected to some degree that if you take the same model, you just change the random initialization and you shuffle the data sets during training, maybe you would have some form of agreement because all these models still learn fairly similarly. But the picture does not change actually when you take different neural networks, like a ResNet, a DenseNet, a convolution net, a non-convolution net, and so on. Naturally, you see that the accuracy maybe fluctuates a little bit more because some models perform better than others, but the agreement is still present to a similar degree in the sense of that these different models get the same sort of samples correct at similar points in time, kind of in correlation to what we've seen earlier about the discussion on shallow versus deep embeddable examples, but kind of like intrinsically based on just a single model. Like a sort of not a single model, but like a single family of models. And we could then do an outlook to maybe close the circle here about the question of then difficulty, and could ask ourselves, could this agreement, despite the randomly shuffling, despite different architecture that we use, could this inherent agreement that is established during training somehow be related to some of the notions of difficulty with which we've started at the beginning of this lecture? And so an experiment that we can make is we can take these curves on particular data sets, again, the red curve being the accuracy, the blue one being this agreement, the green one being some sort of lower bound of like what would be the worst case agreement or the expected agreement that you could guess. And we could now see how the examples that are agreed upon, what their basic statistics look like. So in this example, it's an image classification example on the Pascal dataset. The average entropy of all the examples that were agreed upon by the different neural architectures has been calculated in the yellow curve. And interestingly, we can see that as the agreement rises, as the accuracy rises, so does the proportion of the entropy present in the images. Given that entropy is a sort of a primary measure of how cluttered an image is, somehow this loops back to the start, that although we've potentially said that things like non-centeredness, entropy, and size of objects, etc., are perhaps not that important or not as important as expected for human perception, this is an interesting take now that it seems that these factors do actually come into play quite strongly when we just let the model train itself without interfering, in the sense of that even though we shuffle data, the examples that have low entropy seem to nevertheless been trained first, and the examples that have high entropy get trained towards more the end of the training. And so interestingly, this is not exclusive to entropy. This seems to stretch across various of these, let's say, intuitive statistics. Like you can see the same here for segment count. You can see the same here for frequency of, like the frequency coefficients, so which frequencies are taken into account. You can see this for number of instances and bounding box area as a measure for like how large the objects in an image are in a relative perspective of overall image. So I'm going to maybe wrap up on this slide here because it's quite a, let's say it's quite a novel thing. It's an outlook. And I think what I would like to mention is that there are two things that are really important for curriculum learning. It's the idea of how do we assign a difficulty score. We've started with the notion of let's take very intuitive statistics to define difficulty. We've seen that maybe human difficulty or whatever way we measure human difficulty may not necessarily be directly helpful to the full extent. But we've also now come around at the end to see that difficulty perhaps is something that models themselves can tell us, and something that the models, I mean, sorry for the wording, models themselves can tell us sounds like I'm one of these people talking about AI, like how models are sentient. That's not what I mean, but like we can infer from models what is difficult for a particular sort of hypothesis class, for a particular style of function, for a particular data set and task directly, rather than only constraining ourselves to predefined notions of difficulty. But also, I think we're getting to a degree where we are starting to form more of an understanding that these statistics that we can formulate for various data sets may in fact really be important for curriculum learning after all, giving a little bit of post hoc support why our motivating example of sentence length and word frequency has in fact worked so well on the language example. On the similar side, the pacing maybe is a slightly more difficult question where it seems like pacing, at least to the best of my knowledge, is not as figured out as we'd like it to be. The idea of self-pacing seems to be really nice, but still has some barriers to maybe be overcome. However, again, it's interesting that we can perhaps here use models themselves to identify the pacing. And in particular, it seems that we can make use of like these teacher style pacings and these, I'll call it self-taught / boosting style pacings as well. And so as a disclaimer, as you can see on the slide, there are some really cool takeaways in the sense of that curriculum learning is really useful. It's really important actually to think about. It's kind of the element we've never really talked about so far, because whatever we've visited in terms of active learning, in terms of corset rehearsal, has always been more on the perspective of how important is an example, like how important is it to retain it. But now we're also asking ourselves the question, how difficult is an instance actually for the task and data at hand? And so as a final note, obviously there's much we don't know yet, so it's a very interesting idea to explore this. It's an even more interesting idea to start taking into account the ideas of curriculum learning into the open world learning idea that we've discussed last week. It's in there somewhat implicitly, but I think it needs to be made explicit, and it would be really nice. And so as a very final note to end today's class, we've now seen yet another paradigm in the sense of machine learning. And so if you look at the survey on curriculum learning paper, you'll see that they have all these diagrams of like what is traditional machine learning, what is transfer learning, what's multitask learning, continual learning, active learning, curriculum learning. We've walked through all of these right now. And somehow my idea is still, if you follow the evaluation lecture closely, that it's really a lot about just the setup and specific evaluation niche. In particular, if you take a look at what is here in curriculum learning and, for example, continual or active learning, the differences here are rather minute in principle. There's no sort of conceptual, completely different take. It's once more, again, like if people write a a curriculum learning work or a specific system emphasizes curriculum learning, it's that the idea and the notion of difficulty and pacing takes on the key role and is the key thing that is being evaluated, whereas the other aspects are maybe not neglected, maybe partially even neglected, but not prioritized in that sense. So once more, the key message is that curriculum learning is not just like a thing in itself. I think it's interesting to take into account as a general idea, even when we think of continual learning and active learning and transfer learning, because difficulty and training according to some difficulty that makes sense is perhaps required or at least beneficial. And so again, it's not necessarily one versus the other. Ideally, at some point, it will be converging these different paradigms into one broader take, because all these elements are interesting and important for machine learning in the wild, machine learning in practice. And with that, I'm at the end of today's lecture. I said I was slow today. I said I was fast today, but actually it seems like I'm more or less right on time. I hope you enjoyed it. I hope you got something out of it. And next week, we'll continue to talk about a slightly different angle. More or less, we've now finished the, let's say, grand scheme of perspectives on machine learning. So as illustrated on the slide, we've walked through the majority of these. And so next week, rather than continuing to expand this picture, as it's rather complete already, at least at the current status of the machine learning landscape, We'll start talking about software and hardware a little bit to illustrate the point that these developments are in fact not just purely coming from formulations of mathematical ideas, but actually the development of hardware and software is something that heavily influences and has heavily influenced the development of each and every one of these techniques and paradigms. So I think it's important next week to start taking into account how our field is shaped by developments in software and hardware. And with that, I'm done for today. Thanks for your attention. If you have any questions, please feel free to ask them in chat. Okay, while I wait for maybe one or the other chat question to appear, if not, that's also okay. We'll also, next week, we'll not only talk about hard and software, we'll also have a partial guest lecture, meaning I'll do the first half of the lecture and the second half of the lecture is going to be done from someone else from Continual AI to introduce Avalanche as a coding framework for continual learning to get a little bit of hands-on, to have a little bit more of the coding perspective, given that a lot of you wanted to have some ideas of how we could approach the things we've seen so far in code and practically. So if there are no questions, thanks again for your attention, and I'll end the stream for today. See you all next week.